All right, everybody had a chance to give them a try? Okay, so in the first one, we've got 4 squared being cubed. Sophie, what would you get from that? I don't know. Tell me what you got. What'd you put? 3,024? Where'd my pen go? Oh, there. Sometimes technology works. 3,024. Like that?
She's at 1,000.
Really? Wow. I really messed that one up, didn't I? After all that work and to mess it up. Okay, tell me one more time. 1,024. All right. Anybody agree with that? Okay, Chloe, what'd you get?
4,096.
Put the calculators away. We are not doing calculators.
Or 1,096. Or if you wanted an exponential, 6 powers.
Which you thought was what?
4,096.
Okay, so number 1, you got to do this without calculators. Which means, number 2, we have a question that is always on everyone's mind. How far, to what extent, do I have to work them out? Right? So first of all, exponentially, we're talking about taking a power raised to another power. What do we do with the exponents in that case? We multiply. So in an exponential form, 4 to the 6th power is correct. Okay? But now, would I expect you to come up with 4,096 on your own if you didn't have the calculator? Probably not. Generally, what I subscribe to is what I call sort of the 10-second rule. Okay? It doesn't mean dropping food on the floor and picking it back up and eating it, for those of you for the 5-second rule. The 10-second rule is, can you, within about 10 seconds, work out what the answer is? Okay, if you can, you need to. If it would take you more effort than that, then leave it exponential. So 4 to the 6th is not something I would expect you would probably work out in 10 seconds. It's going to take more effort than that. If it was 10 squared, or 4 squared or 4 cubed, I would say you could probably figure that out. Right? But much beyond a cubed, when you have a base of 4, that's going to take a little more effort. So just leave those exponential. So my 10-second rule basically comes down to 2. Pretty much you take 2 to power up to about 6 or 7. You should be able to figure those out. Multiplying by 2 is not that tough. Okay? 3, you should be able to get up to about 4 or 5. Not that difficult. When you get up to 4 or higher as your base, pretty much if you go to 3 or 4, you're good. Okay? So if you have exponents that are within those parameters, yes, you should be working them out and giving me what the answer is. But if they're beyond those parameters and it's going to take you more than about that 10 seconds to figure it out, then just leave it exponential. So in this case, I would be totally fine with you just leaving this answer as 4 to the 6th. Okay? All right. What happens when I take a negative 8 times a negative 8 cubed? Amy?
Negative 8 to the 4th power.
Like that? Do I need the parentheses around it?
Yes.
Yes. If you're going to leave it exponential, you need to leave the exponents around it. Okay? Now, could I rewrite it in a way that would be equivalent but without the exponent, or without the parentheses? Sorry. Lynn? Just 8 to the 4th. Why would saying just 8 to the 4th be equivalent to having in parentheses negative 8 and then to the 4th? Go ahead. Yeah, why would those two be the same?
Because 4 negatives, negatives is always equal to a positive.
All right, good. So if you want to get rid of the parentheses, then you have to think through what's actually happening here. If I have a negative base and I'm multiplying it by itself 4 times, that's an even number of times. So if I take a negative times a negative, I get positive. Then I take it times another negative, which makes it an odd number, it turns back to a negative. But every time I get to an even number of factors, it goes back to a positive. So when our exponent is even, then we know the answer we should end up with is going to be positive, even if the base started out as negative. So if I want to get rid of those parentheses and clean things up a little bit, then I have to make sure that I'm doing it by making the negative into a positive, not just by getting rid of the parentheses. Okay? Good. How about a fraction like 2/9 being taken to the 3rd power? Chloe, what do you get?
If you use a 10 second, it would be like 2 to the 3rd power negative, because I can't do negative.
Okay, but can you do 2 to the 3rd?
Yeah, so it would be 8 over 200.
Close. Yeah. Because what's 9 times 9? 81. So you can do that, right? So then 81 times another 9. 9 times 1, 9. 9 times 8, 72. 729. So in this case, I think 10-second rule applies. We need this form. We need that one worked out. Now, obviously, the thought process is this first, right? The idea that we take both the numerator and the denominator and cube them separately, and then what would that give me?
Is this 10 seconds ahead, or like can we do it like 10 seconds later?
Yeah, paper, head, like, depends on the situation, yeah. Basically, my point is, what I don't want you doing is spending a lot of time off to the side going 4 times 4, 16 times 4, times 4, times 4, times 4, times 4. Like, no, it's not necessary. But if they're within something you can figure out pretty quickly, you should be doing it. All right, next one, we've got 6 times 10 to the negative 4th over 9 times 10 to the 7th. What is special about those numerator and denominator numbers? What do those look like? Sorry?
There's a negative exponent.
That is true. But if you just look at the numerator, just look at the denominator, what's significant about those? Julie?
Scientific notation.
Yeah, they're looking like scientific notation, right? We've got a number times 10 to a power on the top. We've got a number times 10 to a power on the bottom. That's the form of scientific notation. So in a sense, in this case, we're really trying to divide two scientific notation numbers to see what kind of an answer we would get. So what kind of an answer do we get, Cheryl?
2 over 3 times 10 to the negative 1.
Oh, I want to go back to my green here. 2 over 3 times, what was the rest of it?
10 to the negative 1 power.
Agree with that? Now, if this really was scientific notation, if we were given that context of these numbers being scientific notation numbers, then we probably want to end up with a scientific notation answer.
So these 6.6
Okay?
times 10 to the negative
Okay, so which way does that go? That's the tricky part, right?
Yeah, it's fine.
So the 2/3, we can go, okay, yeah, that's the same as 0.67. We could round it off if we had to. Because we have to change this to a decimal if we're going to say that it's in scientific notation. All right? But there's this little bit about the scientific notation definition that says this number that we're going to multiply by 10 taken to some power, it has to be a number that's between 1 and 10, with 1 included but 10 not included. So keeping it in 0.67 isn't really quite scientific notation yet. Right? So this isn't quite there yet. We're getting closer, but not quite. So we have to change this 0.67 into what Henry suggested was something like 6.67. Okay, well that's better, but now how does that affect this? Is it still going to be 10 to the negative 11th power? No. So what do I have to do to turn this into this? Multiply by 10. So taking 0.67 and multiplying it by a 10 to the first would change it into the 6.67. Well, where's that 10 to the first power going to come from? This 10 piece over here. So what do I have to do to that to get this? I basically have to take one more 10 away from this. Is that making sense? And so it's going to be what? Is it?
I thought it was 10.
All right. So let's approach this a little bit differently. Because the whole idea of taking away and adding gets confusing, right? That's why we're like, is it negative 12? Is it negative 10? So what if we think about it this way? If I started with 0.67, and you didn't know any of the rest of this, I just said, here's your decimal, change it to scientific notation. How would you rewrite it? 6.7 10 to what? Because which way did we have to move the decimal point to get from here to here? To the right. So if you're moving to the right, yeah, if you're going from decimal, I gotta make sure I say this right myself. It's been a while. If you're going from decimal to scientific notation and you're moving your decimal point to the right, then you need negative exponents. If you're going from the decimal form to scientific notation and you're moving your decimal point to the left, then you need positive exponents. Or vice versa, if we're going from scientific back to decimal, negative exponents move this to the left to make it more of a decimal, right? So is that the direction I would want to go from here to get back to there? Yes. So the negative one fits because moving it back this way would get me back to that. Whereas if these are positive exponents, then we end up with bigger numbers, right? Okay, so if I take what I had here, the 0.67, and I now replace it with the equivalent 6.7 times 10 to the negative 1, and then still multiply that by the 10 to the negative 11 I had to start with, now what can I do? Combine the tens by doing what? Adding the exponents. So 6.7 times 10 to the
Oh wait, no, yeah, my bad, yeah.
to the negative 12. That might be the better way to think of it. Take whatever decimal that you have. If it's not in that format where it's between 1 and 10 like it's supposed to be, then just take the decimal part first and say, well, how would I rewrite that into scientific notation? And then replace that in place of the decimal. Take it times the 10 to whatever you had originally, and then combine your tens together by combining your exponents. I think that's a more solid way of doing it, a less confusing way of doing it, to actually get the type of exponent we want in the end. Because it is tough. I mean, you can, I did a really good job of talking Henry out of his negative 12, because he initially said negative 12, and then I went through enough steps here that I had him totally confused, and he's like, I don't know anymore. Maybe it's negative 10, maybe it's negative 12, I don't know. It's confusing, especially when those exponents are negatives. But we've got to make this change. If it really is a scientific notation kind of problem, we need to be giving answers then that are in scientific notation. So we have to make that adjustment if we end up with something that's not quite, by definition, scientific notation yet. Okay? So this is the way I would probably recommend that you go about it. If you're someone who has a little bit of confusion about what to do with those exponents, is just think about, so what happens if I take this and rewrite it just as scientific notation, then replace that in place of this, still multiply by whatever this 10 was, and then combine your tens together to get your final answer. Does that make sense? We're going to see another example of that, so we'll get another chance to see it here in a minute. All right, let's keep going with these. Next, we've got b to the negative 4th times b to the 6th times b to the 7th. Harry, what'd you get for that one?
B to the 9.
B to the what?
9.
9? Everybody agree with that? This is going to be one of the few times in your life where you're actually going to be, thank God, it's just variables. I don't have to worry about whether I work this out or not because I can't. Right? Like, I don't know what B is. I can't work it out, so I don't have to worry about whether to work it out or not. Most of the time we're like, oh geez, variables, seriously? But this is one of the few times where it's like, oh, variables are so much easier. Because you don't have to worry about what the number is and whether I have to work it out. Okay? And even though there's a negative exponent in there, the property doesn't change. The property still is, if I multiply powers together, I just add all the exponents together. So a negative 4 plus a 6 plus a 7 is going to give me a 9. Boom, I'm done. E to the 9. How about r to the negative 2 over s to the third, all taken to the negative 3 power? Henry, what do you think?
I had x to the 6 over.
Where'd x come from?
Was that number? Oh, that's R, my bad, sorry.
Okay, maybe Henry's response is not, thank God it's variables, because he's like pulling them out of the air. It's what?
It's r to the 6.
R to the 6. That sounds better. Over what?
Over s to the negative 9.
Is that what we want?
I like kind
Nope, not quite. Anybody know what the issue is? Amy? Or, sorry, Anna?
We can simplify s to the power negative 9.
Okay, and how would you simplify that?
It would be 1 over s to the power 9. Like, the denominator part would be that. Then
Okay.
if we actually figure it out, it would be s to the, r to the power 6 times s to the power 9.
Yeah.
So, part of the rules for simplifying, one of the rules is that unless we're talking about specifically scientific notation like we were up here, we should not have negative exponents in our final answer. We should only be dealing with positive exponents when we're all said and done. So, we're going to see in just a minute kind of the quick review and the general properties, but hopefully you remember that the negative exponent property is the one that's the reciprocal, right? So the shortcut of that property is that whenever we're set up in some sort of a fraction, whichever side of the fraction bar my negative exponent is on, if I flip that piece to the other side of the fraction bar, I can change it to a positive exponent. So Anna did a great job of explaining why that works. She said that s to the negative 9 is really just 1 over s to the 9th. But if that fraction is in the denominator of our overall fraction, then that means that we can actually multiply by the reciprocal to get it all worked out. So it ends up taking that s to the negative 9th, and it flips it up to the top with our r to the 6th to turn it into s to the positive 9th. So the trick, the shortcut to that property is flip it to the other side of the fraction bar. Wherever it is as a negative, flip it to the other side to make it positive. Yeah?
So if R was 10 to the 6 power and S is to the 9 power make it 6 down, so it would be 1 over.
Correct. Yep, exactly. Yeah, here.
For the fourth one, with 6 times the other one, wouldn't it be just 2 over 3 times 10 to 11?
10 to the 11th? I don't think so, because what do we do with exponents when we are dividing?
Because doesn't the 10 to the negative 4th bar move down to and add with 10 to the 7th?
It could, but then that makes it in the denominator, right? And if we're doing scientific notation, I don't want to end up with that in the denominator. I want it back up on top. So to get it back up on top, we'd have to make it minus. Or the property that says if I'm dividing, I take negative 4 minus the 7, and I just get the 10 to the negative 11th that way. Okay? All right. Negative 2 to the 6th power. What does that give us? David? 64. Agree? How should I fix it? Negative 64. Why is it negative and not positive? Because William just gave a great explanation about how if it's even exponents, we can make it positive, and life is good, and now you're telling me 6, which is even, is giving me a negative 64. Julian?
Is without the parentheses around the negative 2. 2 is the base, and then the negative is outside of it. So
Bingo. Excellent description. Yep. It's all about the parentheses. Forget that base song. It's not about the base. It's about the parentheses. Which I guess you could say it is all about the base. Because technically what Julian said, what is the base? I can't believe I'm saying this, but it's all about the base. What is the base? 2, not negative 2. If the parentheses aren't there, the negative's not part of the base.
PEMDAS.
Okay, the negative comes afterwards. It's like negative 1 that's getting multiplied to whatever 2 to the 6th is. So PEMDAS says exponents first, then we multiply. So the exponent gave me 64, and then I multiply by the negative 1, which gives me the negative 64. But this is going to be what?
64.
This is the 64, because what's my base? The negative 2. The parentheses make the negative part of the base. So now William's description of even exponents giving me positive answers fits. And that's why it works here, because that negative was still inside of the parentheses as part of the base. So it really is all about the base. Oh my gosh, I can't believe that fits. Okay. So, really quick, because our bell's going to ring here in about 2 seconds. Here's the properties in general. I don't want to go through all of them because I want to show you one more quick thing. But is there anything about these properties that you don't remember? Any of these that don't look familiar to you? A to the 0 is always what? 1. If we have negative exponents, we just talked about that. That's the same as saying 1 over a to the positive, so that's the reciprocal one. We multiply, we add. What do we do with this one? Take each one to the m, good. Here we subtract, here we take each one to the m power. Everybody remember those? Okay. Now, the last thing I want to show you here really quick. What you're going to see in homework is going to get a little bit more complex than what we were doing here. But if you just follow the properties, you can get it. Okay? Here's another scientific notation kind of situation, but a real life. And I just want to show you really quick. If you have this swarm of locusts that contains 85 million locusts, do you understand that that is this? Okay? And then that's per square mile and could cover an area of 1,200 square miles. Right? I don't know about you, but how many of you want to do this with all of those zeros? No. All right? So here's a great place to use scientific notation. Say, well, I'm going to make this 8.5 times 10 to the 7th. And I'm going to make this 1.2 times 10 to the 3rd. And then use properties. Okay? The 10s can be multiplied together by adding exponents. We take 8.5 times 1.2, and boom, we've got a great scientific notation. There's a couple of those in the homework as well. All of it's on Canvas. All of it's due for Friday. Enjoy your PSATs tomorrow. We'll see you on Friday.
Oh, these quiz grades. Quiz grades that
How do you realize that one foot's missing? We have 11. I know. Well, only one.
You know what it sounded like you said up here?
What?
Nobody's going to notice if one foot's missing. It's like, what are you talking about? Nobody needs a foot. It's no big deal.
We have 2, so
You got 2. You can get rid of 1. It's no big deal. See ya. Oh.